Hello and welcome to today's daily Leetcode challenge. Today we'll be solving question 287. I have to say I had some technical difficulties before when I was initially recording this video because I was trying something new with drawing this solution. So we're actually not starting from a blank slate. We're starting off with an example of a wrong solution that I'm going to explain why it's wrong. But Nevertheless, we're trying something new. I want to see how I am with drawing these sorts of problems just because it's really hard to always be typing out these examples. Um, and yeah, so we'll go through the solution. Um, I'll come up with a um, couple of maybe edge cases and draw them out, and then at the end of the video, be sure to stick around for that because that's where we'll be comparing our solution to the solution of others. With that being said, let's read the problem. And so here we have question 287. Find the duplicate number. Find the duplicate number. So given an array of integers, nums containing n plus 1 integers, where each integer is in the range of 1 to n inclusive. So again, if we have the example here is if we have integers 1, 3, 4, 2, 2, that means that, so these examples here, 1, 3, 4, 2, 2, that means that n would be, what would n be? N would be, oh, well, 5, so, wait, sorry, n plus 1 integers, so 4, n would be 4, and the range is from 1 to 4, right? So, yeah, let's see, range 1 to 4, cool. Continuing the problem, there is only one repeated number in nums. In this example, it's the number 2. Return this repeated number. So on the return value, we would get 2. You must solve this problem without modifying any nums and uses only modifying the array nums and uses only constant extra space. Okay, so things like sorting the array or using set or some sort of hash to go through all of these values before finding the duplicate are completely out of the allowed sort of solutions, right? So we have to find a clever way to basically to find this duplicate without maybe even iterating over all of them, but that's jumping ahead. So cool. So as the example, we have 1, 3, 4, 2, 2. I'm gonna write this out. 1, 3, 4, 2, 2. Let's see how maybe we can even think about this. So one very common approach, right, is to maybe just go through each one of these numbers, 1, 3, 4, 2, 2, and maybe put them into the set. But again, that's out of the picture. Sorting them would also allow us to find the number in n log n, because, or actually n squared log n, right? Because sorting is usually n log n, and then one more iteration to, oh no, actually it would just be n log n, right? Because 2n log n doesn't actually, the constant goes away. But here's my proposition, right? So if you've ever solved the problem of finding a a cycle in a linked list, something along the lines of this, then maybe this could maybe give it away a bit. What I'm proposing is we actually treat input uh, this input array as just a set of nodes numbered through by their indices, right? So 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4, and 5, right? And here we have in the 0th 1, 2, 3, 4, and we actually don't need this one, right? Cool. And then maybe the edge would be representing where this node is pointing. So it would be a directed graph, or another word for linked list. Let's see, 0 is pointing to 1. 1 is pointing to 3. 2 is pointing to 4. 3 is pointing to 2. And 4 is pointing to 2. Let me redraw this quickly for it to be a bit prettier. We have 0, 1, 2, 3, 4, 0, 1, 3, 2, 4, and the graph looks a bit like this. 3 is pointing to 2, 2 is pointing to 4, 4 is pointing to 2. Right away, this should give sort of away the answer. And I'll link a video that is identical to this one up here right now. I believe it was 142. I don't remember. But yeah, that's my proposed solution. Represent this input array as just a linked list that has a loop. Now, question is, why does it need to have a loop, right? We have this supposed linked list, but what actually makes it what actually makes it or sorry, by looking at this linked list, what gives away that maybe one of these nodes has the same value? Well, what I want to focus your attention on is on these linkages, on these edges. These edges represent what the value is in the array, right? And so basically my statement that I want to make is any node or edge, any vertex text with two word edges is the integer that appears twice. Integer that appears twice. So that's my first statement. Now another someone who might be a bit more careful and thorough with this example could propose a situation that I'm about to draw out right now that has more than one linked lists in the input array, right? Let's pretend that we have, let's say, 10 values now instead of just 5. We have 0, 1, 2, 3, 4, 5, 5, 6, 8, 9, 10. It's actually 11, but that's okay. We'll be drawing these edges from now on. 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, my claim that I will write here later in a second um, is that I cannot draw these edges any way to avoid having this specific edge or this specific um, vertex in the same how do you say this, in the same linked list with the right solution. My claim, again, I'm repeating, is that I cannot have this edge right here, this vertex, oops, I cannot avoid having this vertex in my solution. It will always be in the linked list with the solution. And let's try drawing some potential graph, and then maybe we'll even translate it to a to an array. So here I have a loop, a linked list that has a cycle in it. Really cool. I'll have another linked list. Now notice that each edge only has one outgoing, each vertex only has one outgoing edge. Now why is that? Well, just because of the nature of the array, right? Each index can only hold one number. And so these edges, they actually just represent these numbers, right? So cool. Now let's draw the final cycle, and just notice that I'm drawing these completely randomly. This is just one example, but they could be many. Now, how can I draw an edge from this vertex such that I don't all of a sudden create a subgraph, like maybe one like this, or another one, maybe one like this, right? Where I don't have a vertex that has two edges pointing into it. Can I even do that? Well, I'm claiming that no. And I'm claiming that that is my second point that I'm going to write down. But for now, let's pretend that this is my this is what I've came up with. This is the example that I've came up with. And so my second claim is that I cannot avoid having zeroth vertex in a subgraph that contains the solution. So cool. Now that I have these two statements, let's quickly, just as an example, draw out what this input would look like, and then we'll validate it with our code. So 0 is pointing to 8, 1 is pointing to 2, 2 is pointing to 3, 3 is pointing to 1, 4 is pointing to 6, 6 is pointing to 7, 7 is pointing to 5, 5 is pointing to 4. Oops, no, 7 is pointing to 4. 7 is pointing, oops, I messed up. 7 is pointing to 5. 8 is pointing to 10. 9 is pointing to 8. 10 is pointing to 9. Well, this would be my representation of this graph right here. And as you can see, I've done this just backwards. This would be the graph that we get when we this would be the graph that we get when we have this as the input array. Now, why is 0 not have any input? Why does 0 not have any input edges? Well, because of this constraint here that I've maybe on purpose didn't well, no, obviously it wasn't on purpose. I just didn't say anything about it initially, but that is what allows us to basically come to this decision, right? And so from now that we've basically decided that starting at the 0th index will guarantee us a solution, we can get to coding. And so I'm going to leave this board now behind and implement my solution. Now, this is just me showing that a simple set wouldn't work, but let's begin coding. So the approach here is to have 2 pointers, one slow and one fast. And I've already explained this in the previous solution, so please, in the previous video, so please watch that. But yeah, let's just begin. Fast is equal to 0, while true. We'll end up getting out of it anyway. Slow is equal to nums slow. Fast moves at twice the speed, so we're giving it some extra boost by jumping one more than slow. And now, while slow does not, if slow equals fast, if we have all of a sudden encountered a node that is the same, we're going to get another slow variable that's going to start at 0. And again, this is all going to make sense if you watch the previous video. I'm going to say that while slow does not equal slow 2, slow equals nums slow, slow 2 equals num slow 2. Cool. And so what this should do is return slow. What this is going to do is take two pointers, one slow, one fast, get into a cycle, get into the cycle where the slow catches up, or sorry, the fast catches up to the slow in another loop. And then as soon as that point hits, that means that we are exactly across, or exactly the tail length modulo the, I don't want to mess up here. Maybe I will just show you how it works and why this works, but for now, this is the solution. Yeah, I'm gonna have to draw this out. So quickly, let's just compare it to maybe some of the top. This is wrong, and I'm getting a feeling that all of these are incorrect. No, this one is correct. This is a good approach. Although, I don't know what count is. Set, wrong. Okay, I'm getting a feeling that all of these are wrong. Yeah, they're not going to be good. Let me quickly show you why two slow pointers gets us to the correct intersection point. Pretend that we have a loop, a linked list with a loop. 1, 2, 4, 5, 6. 1, 2. Initially, when we have a slow and a fast pointer, usually referred to as a tortoise and a rabbit, when we start them off on this race, the tortoise is going to go one by one, and let's see how it was 0, well, 1, 2, 3, 4, 5, 6. So the tortoise is going to make 3 steps. The tortoise is going to be green. 1, 2, 3 steps. The rabbit is going to be red. It's a fast rabbit. It's going to go 1, 2, 3. 3 wasn't enough. Let's go again. Let's have the rabbit go a 4th time. It will now be at this point. So let's say 1, 2, 3, 4. The tortoise is slower and it goes 1, 2, 3. On the 4th step, they end up being on the same, they end up meeting on the same node, which is great. They've caught up. But now, what am I guaranteeing you? I'm guaranteeing that you are not exactly how, if I was to, if I was to have, basically like, just purely visually, if I was to wrap these two alongside, like put this one next to this one and this one next to this one, you would see that these two are sort of just an extension of where they would have been if they were wrapped right alongside the the cycle. And so what that allows me to do is actually just, once I have the tortoise set up at the right place, I can start another tortoise. Oops. I can start another tortoise on a journey from the beginning. Let's have this tortoise be, I don't know, yellow. So the tortoise is going to go 1, 2, and this green tortoise is going to go 1, 2. You're guaranteed to end up at the start of the cycle. And guess what? The start of the cycle is exactly the number that repeats twice because it has 2 edges going into it. So here, the same idea. The tortoise and the rabbit, they start on this node. They go into this loop and they eventually find themselves on the same node. At that point, I start another tortoise on the first edge, sorry, on the first vertex, and find the start of the loop. And that's exactly why this approach works. So I have the fast and the slow. We first iterate until we end up on the same node, meaning that we've found ourselves somewhere, we've caught up to ourselves somewhere within the cycle. And then I start the slow tortoise, number 2, and go until I find the node of the start of the what do you call it? The cycle. Cool. Well, guys, thank you for watching. I hope that drawing this out sticks around because I'm also a very visual person, and uh, actually I came up with a solution initially just by imagining different linked lists appearing in this input nums array, and obviously that didn't click right away, right? I was looking at maybe imagining these three or four. I was imagining many different cycles, and I couldn't figure out, well, how am I going to figure out which one of those cycles I should actually be looking at? And only after a really long time it hit that um, the zeroth index will always be pointing um, to a cycle that's already complete, right? And if that cycle is already complete, that means that every node, every edge there is already pointing to a vertex. I will be that extra edge pointing to a vertex twice. And there we go. Cool. Well, thanks for watching. Please like and subscribe, and I'll see you later. Bye.